Hello and welcome back. We are in prescriptive analytics and we're going to talk about transportation problems. My name is Hari Rajagopalan and I will be your lecturer for this video. So transportation problems, let's take an example. You will have two types of what we call as nodes. One are called supply nodes, which are supplying material, and the other one are called demand nodes, which actually receive stuff. So you have something which sends stuff and you have something that receives stuff. So let's take an example problem here. We have Tropic Suns, which is a grower and distributor of fresh citrus products, and they have three large citrus groves. They have Mount Dora, Eustis, and Claremont. So these are supply centers. And so these supply centers, you got to have some material there. So they have 275,000 bushels of citrus in Mount Dora, 400,000 at Eustis, 300,000 in Claremont. The company has citrus processing plants in Ocala, Orlando, and Leesburg. And now these are demand locations where you receive stuff, these processing plants. And they can handle 200,000, 600,000, and 225,000 bushels. So that's the demand in these areas. And so they contract with a local trucking company to transport its fruit from the grove to the processing plant. And the trucking company will charge a flat rate for every mile that each bushel must be transported. So a bushel of fruit travels is known as a bushel mile. And they want to determine how many bushels to ship from each grove to each processing plant in order to process all fruits while minimizing the total number of bushel miles the fruits must be shipped. Because if they're going to charge, let's say they charge $1 per bushel mile, then the less bushel miles, the less money they end up paying. So it's a minimization of cost. So let's look at this table. And this is essentially what we have. So Mount Dora to Ocala is 21 miles. Orlando to Mount Dora is 50 miles. Leesburg to Mount Dora is 40 miles, and so on. And here we have the number of, this is the supply, and here's the demand. So we're going to model this problem. So first thing you got to do in a transportation problem is to actually, you're going to add up all your supply. This is 975,000 total supply, and total demand is 800 plus 225. It's about 1,025,000, right? So this, in this particular case, demand is greater than supply, and we'll talk about situations where supply is greater than demand, supply is less than demand, and supply is equal to demand. So here, let's visualize the problem. We have these three groves, which are supply nodes. Here is the supply. Here's the amount which we have. That's 975,000. And here are the processing plants. Here is the demand. So rather than capacity sounds kind of, sometimes capacity, what happens is when you say capacity, in this particular case, it is the capacity. However, it gets confused. Let's just call them demand. So this is the demand, and let's go ahead, and now that's 1,075,000. So definitely your supply is less than demand here. And here we have the distance in miles given, and that's what we want to, each of these arrows here is what gets sent. So what gets sent from Mount Dora to Ocala and so on. So let's think through this problem. So let me get a pen here so we can think through this problem. So we have, if you think about it, we have a variable, let's call it xij, right? So it's a two-dimensional variable where we have, let's say x14 is number of bushels to be sent from one, in this case, one is Ocala, to 4. And 4 is, if we look at this, let's get the Uh, so 4 is, oh, sorry, 1 is Mount Dora, 4 is Ocala, right? So we can go through this each one. So we kind of go, I is the supply node, J is the demand node, and we're sending these bushels through, okay? So now it's pretty easy because now we can multiply the bushels times the miles to get the bushel miles, okay? And that's where we have this, you have your objective function, right? And of course, then your supply, we'll talk about the supply constraints and the demand constraints. So in this situation, we're going to have constraints on each one of these nodes. So each one of these nodes has arrows. So node 1 has 1, 4, 1, 5, and 1, 6. Node 2 has 2, 4, 2, 5, and 2, 6. Node 3 has 3, 4, 3, 5, 3, 6. Also, the receiving nodes has 1, 4, 2, 4, 3, 4. 1, 5, 3, 5, 2, 5, and 3, 5. And 1, 6, 2, 6, and 3, 6. So that's the receiving node capacity. So here supply is greater than demand. When supply is greater than demand, then you are going to send all this 975,000 over, right? Because they're asking you for 1,075,000, not 9. So you're going to send everything over, and this here you're not going to be able to satisfy demand. Okay, so we'll walk through this problem. So we have Xij is the number of bushels shipped from node I to node J. And so there are 9 decision variables. And so here are the decision variables you have. And you're going to minimize the total number of bushel miles. So you're basically multiplying the bushel miles times the number of bushels. The miles times the bushels. And it's subjective. So let's look at a demand constraint. From Ocala, Orlando, and Leesburg, these are your demand, right? You're not going to get the entire 200,000 or 600,000 for all 3 because there is not there's not 1,075,000 bushels. There's only 975. So obviously then when supply is less than demand, your demand constraints all will have less than, right? So you're saying everything that goes, all the arrows that go into Ocala is less than 200,000. And similarly for Orlando and Leesburg. Your supply constraints, on the other hand, will have equal to constraints because you're going to send everything you have. So so all the arrows going out of Mount Dora, 1, 4, 1, 5, 1, 6 will be equal to 275,000. And of course, you'll have non-negativity constraints. So it's important you understand that when supply is less than demand, supply constraints will have equal to, demand constraints will be less than or equal to. Now, if supply is more than demand, that is, let's assume this was 500, it's a 300, this was 500,000. If supply was more than demand, then these supply constraints will be less than, and demand will be equal to. Why? Because you're not going to send everything you have. If you have 1,175,000 and you need only 1,025,000, right? Then you're not going to send everything. You're only going to send what is demanded because it costs you, right? So therefore, this will be less than, this will be equal to. If they are both equal, then both sides will have equal to constraints. So let's go to Excel and see how we're going to set up and solve this problem. I'm going to show you 2 types of setup. The first type is your normal setup, where you basically put all your variables and then first row, leave the first row blank, and then you put your coefficients and so on. The second one is an easier format for transportation problems, and I'm going to show you how to do it. You can choose any setup here. Okay, so we'll start with this. Here is the rectangular format. You see, here is the setup, here is the model, And here you have the Excel setup. It's very similar. You've done this before. You put all the variables here. First row is blank. Second row contains the objective coefficients. Then you have the constraint coefficients. You have the left-hand side, the right-hand side objective function. You're going to use the sum product, so this is pretty straightforward, right? And here you've set it up. But what if you wanted a cleaner setup? Here is an example of a cleaner setup, and I'll show you how to do this. So here I've basically copied the entire data set into a nice little table. It's a nice rectangle. And then you have supply and demand. I prefer to use demand instead of capacity because that's really, these are demand nodes. And the first thing you're going to do is you're going to copy this right down here. All right, so we copy this whole thing. We're going to delete this center, right? And this is, while this gives you a number of distances, this is the number of bushels transported, right? That's basically what you have here. I'm just going to, as you know, I'm obsessed with formatting. So instead of demand, we change, let's call it received, and instead of supply, let's call it sent. So here we are going to do sum of these three. Here is what you're sending. I'm going to copy, paste formula. Similarly, what you received is the sum of these three. And then you're going to copy and paste formula. And then you have cost, which is the sum product of this, comma, this. So here is what you're going to have, the total cost. All right, so let me go ahead and format it. So when you go to optimization, your objective, this is your objective. So you don't want to maximize it, you want to minimize it. And your variables are, these are your variables. Your constraints are this left-hand side, which is the sum of whatever is being sent. In this particular case, will be less than supply. Sorry, will be equal to supply because you actually have supply is less than demand. And whatever you received will be less than your actual demand. You go to engine, assume non-negative is true. Make sure automatically select engine is selected, and then you click and you get your answer. Okay, so this is a easier, shorter way of setting up a transportation problem than this. However, this requires a little bit more knowledge. This one, so once you finish the math model, you can just blindly put stuff in. So we walked through Excel, and I'm going to kind of show you the model when supply is greater than demand. So when supply is greater than demand, take an example here. We have demand is 800 million 25, and here this is about it's a million 100,000, right? So in this particular case, total supply is 1.1 million and total demand is 1.075 million. And so nothing changes except your demand constraints now are equal to Y, because you'll be able to satisfy everything that you demanded. And your supply constraint will be less than, because you're not going to send everything over. Okay? And that's essentially when supply is greater than demand. When supply is equal to demand, here supply is 1.075 million, demand is 1.75 million. Demand constraints equal to, and supply constraints is, you can actually use equal to here. You don't have to do less than equal to. Less than equal to will not be wrong because you'll send everything. So you can just put an equal to sign here. All right. And that's it for a transportation problem.